We're doing math analysis, chapter 3, section 2, arc length, velocity, and the area of a circular sector. I'm your host, Dr. D. First thing, like we talked about when we first defined the radian, theta equals s over r, so it equals arc length divided by radius. Well, if I multiply both sides by r here, then I get s equals r theta. So that means the arc length equals the radius times the angle in radians. Now, it's important that your angle is in radians because, like I said, it cannot have a unit. So if you multiplied by your angle in degrees, then you'd have to divide by 360. Okay, now, S equals r theta, you need to memorize that and never forget it. Okay, now, next thing, distance equals rate times time. You've known that since Algebra 1. So, basically what that's saying is distance around a circle, s, equals rate, which is velocity, times time. Now, if I divide both sides by time, then I get velocity equals s divided by t. So what this means is the linear velocity equals the arc length divided by time. Or in other words, if you're running around in a circle, well, how fast are you going? That's going to be the distance around the circle divided by the time that it takes you to run. So this is basically your distance equals rate times time in a circle. All right, now, next thing we want to do is we want to talk about angular velocity. See, this is linear velocity here, v. That's how fast you're running around the circle. Well, what I want to know is how many times you're making the circle in a given length of time, or how many radians per second are you turning. So we know that s equals r theta, because we memorized that before. And we know v equals s over t, because we memorized that before. So when we take those things together, and what I'm going to do is I'm going to substitute the r theta for the s. So that means v equals r theta divided by t. Now, this is still linear velocity. Now, the theta over t is what we call angular velocity. Now, this symbol looks like a W, but it's not. Okay, this symbol is a Greek lowercase omega. So it's omega equals theta over t. Angular velocity. Now, angular velocity is basically saying how many radians per second am I turning. So if you have an engine, how fast is your engine spinning? Well, it's in revolutions per minute, RPMs, and you can convert that to radians per second. Or an old vinyl record, like, well, way old vinyl record would be 78 RPM. The 33 1/3 RPM is probably the one you're familiar with, or the single would be 45 RPM. So that's your angular velocity. Now notice what we have here, omega equals theta over t. Well, then velocity equals r times theta over t. That means velocity equals r omega. And the units of omega are radians per second, or remember, radians are unitless measure, so really, more properly, units of omega would be just simply per second. Okay. it would be a really handy idea if you had these 4 formulas memorized.
That's the smartest thing I've ever heard anyone say about anything.
Okay. Okay, next, the area of a sector. Now, you may remember from geometry that a sector is a portion of a circle, or it's like a slice of pie. So how do we find this yellow area here? Well, the area of a whole circle is pi r squared. And you know that the angle of the entire circle is going to be 2 pi radians. So, pi here, if I solve for pi, divide both sides by 2 or multiply both sides by half, so pi equals 1/2 theta for the whole circle. So that means area, if I substitute the 1/2 theta in for pi, it's going to be 1/2 theta times r squared. Now that's a valid measurement for any theta value or any portion of a circle. So that means area equals 1/2 r squared theta. 1/2 r squared theta is the area of a sector where theta is the angle measure in radians. So once again, would you want to actually memorize that?
That's the smartest thing I've ever heard anyone say about anything.
Okay. So, cruising onward. Let's take an example. We have a circle with radius 8 inches. So we want to find the arc length of that 8-inch radius circle when theta is pi over 4 radians. Well, first let's look what we're talking about here. So here's our circle. And we're told that the radius is 8 inches. And we're told that theta is pi over 4 radians. Now, where is pi over 4 radians? That's what we used to call a 45-degree angle. So basically, we're looking for the area, or no, I'm sorry, we're looking for the arc length. So we're looking for the length of that arc right there. Okay, so how do we do this? Well, we know that S equals r theta. So that means S equals 8 inches times pi over 4. Now, I don't need to put pi over 4 radians because remember, radians is not a unit. So 8 times pi over 4 ends up equaling 8 divided by 4 is 2 pi. And what are the units? Inches. 2 pi inches is the length of that arc. Now, we could do a decimal approximation and say it's approximately 6.28 inches. Now, anytime you're finding lengths or areas, you should stop and make sure it makes sense. So if this is 8 inches here, does it make sense that this arc length would be 6.28 inches? Yeah, because it's a little less than the 8, so that's fine. Okay, cruising onward. This is an interesting problem. Quito, Ecuador is at 0 degrees latitude, which means it's on the equator, and 78 degrees longitude. Now, I have no idea how to pronounce this town in Brazil, but I think it's Macapá. So Macapá Brazil, the accent on the pa, is 0 latitude, which is on the equator also, and 51 degrees longitude. Now, also we need to know that the radius of the Earth is 3,960 miles. With this information, we can find the distance between these two cities. Okay, so how are we going to do that? Well, first of all, let's find the difference in the angle between the two cities. So let me just draw you a little sketch of what we're talking about. Here's the Earth, and we're looking down on the Earth. So basically this blue line is the equator. Okay, so we've got, we'll just say here's 0 degrees right here. And so then we've got 78 degrees right here. And then we've got 51 degrees right there. So to say how far is Quito from Macapá, we basically are asking what's the arc length right here. So go ahead and turn the video off and solve that, and then turn it back on and see if you got it right. Seriously, turn the video off. I know it's still on. I can see you. Okay. All right. So what we do is we say the angle difference is 78 minus 51 is 27 degrees. Now we need to change that into radians because we know that S equals R theta in radians. So what I do is I say 28 or 27 degrees over 1 times, now I'm getting rid of degrees and changing it into radians. So we have pi radians per 180 degrees. So this is, back to my handy calculator, 27 over 180 times pi. So that ends up being approximately 0.471 radians. Now, I'm not going to round off. I'm going to leave that in the calculator. This is my theta. So S equals R, which is 3960 miles, times the radians, which what I'm going to do is I'm just going to say, so I'm not going to type in 0.471 into my calculator. I'm just going to leave what's in my calculator there. So I multiply that by 3960, and I end up with S equals 1866. Yeah, we'll just leave it like that. 1866 miles. So Quito and Macapá are approximately 1,866 miles apart. That's it. Piece of cake. Okay. Now, a standard LP, that means a vinyl record, in case you guys aren't aware of that. Okay, a standard LP rotates at 33 1/3 RPMs. Find the angular velocity. Okay, let's just do this thing then. Okay, 33 1/3 RPMs. What I'm going to do is I'm just going to make this 100 thirds revolutions per minute. That's what RPMs means, revolutions per minute. Now, I need to change it to radians per second. So what I need to do is I need to change revolutions into radians. So I'm going to put revolutions on the bottom because I want to cancel the revolutions. And by the way, that's what they should have done in Cuba back in the 60s, canceled the revolution. Okay, so cancel the revolutions, and now we say there are pi radians in one, or I'm sorry, 2 pi radians in one revolution. Now, I'm not going to put radians up here because there's really, radians are no unit. So now what do I have? I have, the radians are gone, I just have 100 thirds times 2 pi per minute. Well, I don't want per minute, I want per second. So I need to get rid of minutes. So I put minutes on top to get rid of minutes, and I put seconds on the bottom. There are 60 seconds in 1 minute. Now I'm ready for the calculator. So all I do is multiply across the top, and I have 100 times 2 pi. So that's 628.318530718. And then divide by 3 times 60 is 180. And so I end up with 3.49065. So 3.49 radians per second, or 3.49 per second. This is the angular velocity of a standard LP. Okay, now, next step, let's say a fly lands on the vinyl, exactly 4 inches from the center. What I want to know is, the fly's sitting there on the record while the record's turning. How fast is the fly going around in circles? Basically, what's the linear velocity of that fly sitting on the record 4 inches from the center? Well, let's do this thing then. What was that formula that you memorized? Ah, that's right. It's velocity equals r omega. Okay, so the velocity of the fly is going to be r, which is 4 inches, times omega, which you already have in your calculator, is 3.49. Yeah, let's just write this out here. 3.49065 50399. Now, what are the units? Per second. All right, now when we multiply this, and you wouldn't punch this all in, you just leave it in your calculator, just multiply by 4, and that ends up being, velocity is 13.96. Now, what are the units? Inches per second. Inches per second. Now, that is a legitimate velocity for the fly, 13.96 inches per second. That fly is cooking. Okay, let's check that out in feet per second. Okay, if I want this in feet per second, then what I need to do is get rid of inches. So what I'm going to do is put inches on the bottom and put feet on top, and there's 12 inches in 1 foot. So when I multiply this out, basically I'm going 13.96, which is in my calculator, divide by 12, and it's 1.16355, so 1.16 feet per second. Now, what if I want to know how many miles per hour the fly is going? Well, then I go 1.16, and remember, I'm just keeping this in the calculator, so I'm not really punching in 1.16 feet per second. Now, I need to get rid of feet, so I put feet on the bottom. And I need to turn it into miles. How many feet are in a mile? How many feet are in a mile? Okay, you might think that's some obscure question. That is something that every educated human being in the world should know. And don't ask your parents, because they probably don't. Okay, so 5,280 feet in a mile. So all I do then is I'm canceling feet. Now I've got miles per second. Well, I don't want miles per second. I want miles per hour. So I need to get rid of seconds. So I put seconds on top since I have seconds on the bottom. And I put hours on the bottom. Now, 1 hour is 3,600 seconds. So what does this give us? Well, I have the 1.16 in the calculator. I multiply by 3,600. And I divide by 5,280. And that gives me 0.793 miles per hour. So if the fly is on the vinyl record 4 inches from the center, it's traveling, let's see, yeah, it's traveling 13.96 inches per second, which is 1.16 feet per second, which is a little less than a mile per hour. Okay. Cruising onward. How fast is the tip of a second hand moving on a clock if its length is 15 millimeters? Okay, that's interesting. How are we going to do this? All right, well, let's look at it. We've got the length of the hand is 15 millimeters. And we know we're being asked for how fast, what is the velocity of that? So velocity equals r omega. Well, now we need to know what omega is for a second hand. Well, how fast does the second hand move? Well, it's going to rotate 1 time around in a minute. So that means omega is going to equal 1 revolution per minute. Now, we need to get this into radians per second. So, 1 revolution is 2 pi radians. And 1 minute is 60 seconds. So that means the angular velocity, notice the revolutions cancel, the minutes cancel, and I'm left with simply radians per second, or just per second. So if I multiply this out, it's going to be 2 pi over 60, or just pi over 30, per second. So that's 0.1047. I'll just say 0.105 per second. All right, now, we know that V equals R omega. Now let's say we forgot that formula. We forgot that formula? Okay, shut up. Okay, we forgot the formula, let's just say, hypothetically. All you have to do is say, well, I've got millimeters and I've got per second. What should I do to get velocity? Well, I want millimeters per second, so I just multiply those. So it's just going to be velocity equals 15 millimeters times 0.105 per second. And so that velocity is going to be, now all I do is keep the 0.105 in the calculator and I just multiply by 15. So it's going to be 1.57079,63268 millimeters per second. So 1.57 millimeters per second. Now, if the hand is 15 millimeters long, then it makes sense that it would be traveling 1.57 millimeters per second. Now, if the hand was 15 feet long, so this is a huge clock, now we would have 1.57 feet per second that it's traveling. Okay, so one last example problem. We want to get the area of a sector with central angle pi/5 and radius 8 feet. Okay, so we've got our circle. The radius is 8 feet. And the angle is pi/5. Well, I know that pi/4 is about 45 degrees, so pi/5 would be slightly less than that. That's a little bit too small, but we'll go with it. So here's the sector that we're dealing with. So what is the radius of that sector? Well, I mean, what is the area of that sector? Area equals 1/2 r squared theta. So that equals 1/2 times 8 feet squared times pi/5. And notice no units required here. So that's it. I just have to crank that out. So 1/2 times 8 squared is 1/2 times 64, which is 32. And 32 divided by 5 is 6.4. So it ends up being 6.4 pi square feet. And yeah, we'll just multiply that out. 6.4 times pi is 20.106. So 20.11 square feet. That's it, piece of cake. So, have fun with these.
That's all, folks.